Hey everybody, welcome back to my channel on Feynman integration. No Feynman integration today. We're going to be developing a tool that we'll be using in later videos. And what we're going to be doing today is evaluating the Basel problem. Basel problem, I'm not sure. But anyway, the Basel problem asks this question. What is an exact value for the following? 1 plus 1 over 4 plus 1 over 9 plus 1 over 16, forever. In other words, what is the sum of the reciprocals of the squares? So the first thing we're going to need to know to solve this, and this is just where we're going to start, we're going to need to know the Taylor series expansion for the sine function. And that's this. We know that the sine of x is equal to this. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and on and on and on forever. All right, so since we know that, just do the same thing to both sides of the equation. We'll just divide both sides by x. So we're going to have a 1 here, and this is going to change to a square, that'll change to a 4th, that'll change to a 6th. So we're just going to have 1 squared to the 4th to the 6th. So we know that's true. All right, well, how does that help us? Not so much right now, but this is just an infinite polynomial, and we know polynomials can be factored into a bunch of terms. It's going to have n roots. In other words, there are infinitely many values for x that you could plug into this equation to get you 0. 0 is a place where this x will give, plugging in a certain value for x will give you 0. That's called a root. So it's very difficult to figure out the roots from just looking at this side of the equation. However, we know the sine function looks like this. We'll just draw the x-axis right there. Here's the y-axis. And it looks like this. So we've got zeros here, 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 everywhere. We just have infinitely many roots. And that, that checks out because we have infinitely many terms. So we're going to have infinitely many roots. All right, what are those roots? Well, we've got 0, we've got pi, we've got 2 pi, we've got negative pi, we've got negative 2 pi. In other words, we have roots at n pi. Okay. Well, how do we express those roots in an infinite product? An infinite product is going to look something like this. Well, it's going to look like this. It's going to be one term times another term times another term times another term, forever. Okay. Let's just look at this for a second. How are we going to recover a 1? Remember, whatever this times this times this times this is equal to, it has to equal this. And this contains a constant value of 1. Whatever other x squared and x cubed and x to the 4th terms you have, you know that you're going to pull out a constant of 1. You're going to have a 1. So how can we get that? I mean, without using without doing some crazy stuff like this, like 1/2, and then you have a 2 here, and then you have a 1/2, and then you got a 2 here. I mean, maybe you could recover a, I don't know. So you just have 1 times 1. Yeah, you could recover a 1 that way. But why make it that complicated? Why not just put 1 as the leading term in every one of these factors? We will definitely recover a 1 as the result of the first term times the first term times the first term times the first term. It's just going to be 1 times 1 times 1 times 1 times 1, which is going to give you that 1. All right. Now, how do we show these roots? Remember, we have roots at x is equal to n pi. So we know that basically means if we plug in 0 for this, we have to get 0. Well, let's see. We could just have, well, let's ignore that for now. We know that if we plug in pi, we're going to get 0. So if we plugged in pi to that term, we'd get 0, right? If we plugged in pi for x, we'd get pi over pi, which is 1. 1 minus 1 is 0. Also, we could get a 0 like this, plus pi over x, right? Because we know that negative pi is a root, and if we plug in negative pi, we get 1 minus pi over negative pi. In other words, 1 minus 1. In other words, 0. Let's keep going. We also could get a 0 like this. Hold on. We could have 1 minus 2 pi. Or, I'm sorry. I should have written it like this. X over pi. Although it is true the other way as well. This is just going to be easier to work with. X over pi. And of course, we'd have a root at 2 pi. And if you plugged in 2 pi, you would get 0. That's what a root is. Also at negative 2 pi. Yeah, so we have basically an infinite product that's going to look like this. Just 1 minus x over pi times 1 plus x over pi times 1 minus x over 2 pi times 1 plus x over 2 pi, and so on forever. Well, you'll notice that it's very easy to combine this term with this term, likewise this term with this term, and all the successive terms like that. These two terms would multiply out to be, we would have 1 minus x squared over pi squared. These two terms would be 1 minus x squared over 4 pi squared. And if we continued this, we could continue this one. Our next term in this would be 1 minus x squared over 9 pi squared. And this would continue on and on and on forever. Well, that's a good place to stop for the combining of terms. We're really not going to be able to get a good pattern past this. So that's where we're going to leave it. All right, now we're going to pull a tool from partial fraction decomposition where we match, like, basically we match like terms, like we're going to match up the x squared terms of this with the x squared terms of this. We know they're going to be equal. The x cubed terms of this would equal the x cubed terms of this. In other words, 0 would equal 0 because there are no x cubed terms in there. But the x to the 4th terms of this would also have to match up perfectly with the x to the 4th terms in our infinite product. So what is that? What am I saying really? Basically, we're saying that, let's see, what are the x squared terms in this? We're saying that negative x squared over 3 factorial is going to be equal to the coefficient on the x squared terms when you multiply this entire thing out. What's that gonna look like? Well, let's see. How are we gonna get x squared terms? We could get an x squared term by multiplying this times this times this times the first term times the first term, and on and on and on and on and on together. We could also get an x squared term by multiplying this times this times this times this times this. We could also get an x squared term by multiplying this times this times this. In other words, the x squared terms in this are going to equal, let's see, this times this times this times this is going to be negative x squared over pi squared. Another x term, we could multiply this times this times this times this times this. In other words, minus x squared over 4 pi squared. Likewise, we can recover an x squared term by multiplying this times this times this times this times this. In other words, minus x squared over 9 pi squared. And that would continue on and on and on forever. Sorry. And then just on and on and on and on forever. Okay, those negatives are annoying. So let's erase them. Or at least erase those first two, and then turn these into positives. Okay. Okay. Well, so we know this is true, because that's what we got when we matched up the x squared terms of this with the x squared terms of this. So they are equal to each other. Okay, let's factor out let's factor out an x squared over pi squared from this infinite sum right here. So we have that x squared over 3 factorial is equal to, let's see, we factor out the x squared over pi squared, and then this would be 1. This divided by x squared over pi squared is, let's see, 1 over 4. This would be plus 1 over 9. All right, well, that's exactly what we wanted. And we'll call this I, like usual. So let's see. This is this. It's just 1 plus 1/4 plus 1/9 plus 1/16. So we can just replace that with I. All right. Divide both sides by x squared and multiply both sides. Oh, I'm sorry. This should be a pi squared. So what we're going to do is we're just going to multiply both sides of the equation by pi squared over x squared. That's going to give us pi squared over 6. There you go. That's the Basel problem. It's what that equals to. It equals, kind of looks like a cube. That's not correct. It equals pi squared over 6. And in the next video, I'm going to be evaluating this. The alternating sum of the reciprocals of the squares. So that'll be the next video. And for now, I hope you enjoyed that.